Every thought you have and every movement you make relies on a sudden flash of electricity, and the fuel for that spark is sodium chloride. This diagram of a cell membrane shows exactly how that fuel is processed. A specialized protein acts as an engine, the sodium-potassium pump. It actively pushes 3 sodium ions out of the cell for every 2 potassium ions it pulls in. This unequal exchange creates a steep electrical imbalance, or a concentration gradient, across the membrane. When a nerve signal needs to fire, voltage-gated channels suddenly open. The hoarded sodium rushes back inside, triggering a microburst of voltage called an action potential. If this microscopic exchange of salt stops, nerve transmission ceases, and the heart muscle stops contracting. The entire biological machine halts instantly. Because it is absolutely essential for survival, human biology evolved to fiercely conserve salt in ancient environments where it was scarce. But modern engineering has surrounded us with absolute abundance. When we constantly consume more salt than we need, our physiology hits a breaking point. In this cross-section of a blood vessel, you can see how excess sodium particles exert an osmotic pull, actively drawing surrounding water molecules directly into the bloodstream to dilute the salt. With that extra water, the total volume of blood increases. That excess liquid pushes hard against the arterial walls, creating intense mechanical pressure from the inside out. Our cardiovascular systems are failing because they are forced to process a sheer volume of salt engineered into our daily environment. And yet, human consumption is only a fraction of the total demand. Salt is the ultimate industrial feedstock. The vast majority of the sodium chloride we extract from the earth never gets near a dinner table. It is fed directly into chemical manufacturing and infrastructure. This schematic shows the invisible backbone of modern industry, the chlor-alkali process. It uses a strong electrical current to split a saltwater brine solution, separating it into 3 distinct streams: chlorine gas, hydrogen gas, and sodium hydroxide, or caustic soda. We use those 3 specific chemicals to manufacture PVC pipes, synthesize pharmaceuticals, formulate industrial solvents, and treat municipal drinking water. Modern civilization relies entirely on extracting unimaginable quantities of salt from the earth. Without it, our physical and chemical infrastructure collapses. To meet this massive industrial demand, extraction companies use a technique called solution mining. They pump pressurized fresh water deep underground to dissolve ancient salt beds into a liquid brine, which is then pumped back to the surface. This process leaves behind massive fluid-filled subterranean caverns. The geological vulnerability lies in the nature of the mineral itself. Under intense pressure, salt is highly ductile. It slowly creeps and shifts, transferring immense mechanical stress upward into the brittle layers of caprock sitting above the cavern. Eventually, the immense pressure becomes too much to bear. That overlying rock reaches proportions' critical breaking point, and the cavern's ceiling suddenly snaps. This technical cross-section shows exactly what happens next. A void opens as the roof rock falls into the cavern. That void slowly migrates upward as successive layers of rock collapse, until it breaches the surface, forming a sudden, violent sinkhole. The surface devastation is immense. Here you see the massive north and central sinkholes that swallowed sections of land over an abandoned Michigan brine field. We relentlessly hollow out the earth to extract the salt we need to build our surface infrastructure, literally causing the ground beneath us to cave in. Once we bring all that salt to the surface, it never truly disappears. In the United States alone, over 20 million tons of salt are dumped onto roads and highways every winter to melt ice. When the snow melts, that immense volume of salt washes directly into natural watersheds, triggering a phenomenon known as freshwater salinization syndrome. As this diagram shows, high salinity water creates a toxic chemical cocktail in the ground. The heavy influx of sodium ions actively displaces heavy metals and radioactive materials trapped in the soil, washing them directly into the underground water table. That highly saline runoff flows into reservoirs and actively strips the anti-corrosive coatings inside city plumbing. This exact chemical reaction pulled lead directly from pipes into drinking water, driving the devastating public health crisis in Flint, Michigan. By pouring salt onto winter roads to keep them clear, we trigger invisible chemical chain reactions that poison our own drinking water and decimate aquatic ecosystems. A single salt molecule journeys from the microscopic necessity firing our nerve cells to the raw material of industry, to an underground geological hazard, and finally into an environmental toxin. Through aggressive extraction and unchecked application, industry has broken the natural equilibrium of this vital mineral. To fix this, we have to re-engineer how we interact with salt across every scale, from lowering our dietary intake and adopting alternative de-icing methods to strictly regulating how we mine the earth. Sodium chloride regulates the systems that keep us alive. Until we respect its limits, the foundations of our bodies, our infrastructure, and our biosphere remain on the brink of catastrophic failure.